The microscopic vibration of electrons inside a silicon lattice and the orbital precision of satellite constellations exist on different scales, yet they are governed by the same integrated logic. A modern engineering degree provides an architectural blueprint for navigating these scales, moving from the physics of an atom to the complexity of a global network. We can see this structure clearly by examining the 2025 curriculum for the Electronics and Communication Engineering program at the National Institute of Technology, Patna. Over 8 semesters, the syllabus constructs an abstraction stack. It begins at the bedrock of physics and builds upward. Progressing through this degree means mastering one layer's constraints, then packaging that knowledge to manage the next level of complexity. The true value of an ECE engineer is knowing exactly how a line of software code physically manifests as an electromagnetic wave. This process begins at the base of the stack in semesters 1 and 2, which focus entirely on the physical medium. Manipulating data requires a rigorous understanding of the forces that carry it. Engineering physics and engineering mathematics provide the framework for Maxwell's equations, wave mechanics, and vector calculus. This math leads to the raw material of the digital age. The atomic structure of a silicon wafer determines how electrons drift and diffuse. Semester 3 introduces semiconductor devices, the pivot point where theoretical physics becomes applied engineering. Students translate concepts like energy bands and p-n junctions into tangible components like MOSFETs and bipolar junction transistors. Here, the engineer creates the first level of abstraction, hiding the complex quantum behavior of electrons behind the reliable operation of a transistor. Without this physical bedrock, every digital system or communication network lacks a functioning medium to exist within. Once the physical medium is mastered, the curriculum moves to the second layer of the stack, building logic. Digital electronics introduces a shift in perspective. The engineer stops tracking continuous electron flow, thinking instead in binary ones and zeros. Logic gates like NAND and NOR are combined to build flip-flops and multiplexers, assembling into circuits capable of computation. In semester 4, microprocessors and microcontrollers organizes millions of these logic gates into a functioning central processing unit. Students learn assembly language, the absolute lowest level of the hardware-software interface. This is where the engineer learns to issue commands directly to the physical registers on the microchip. Logic and architecture represent the bridge where physical voltage is transformed into programmable instructions. Perfect digital logic must eventually survive a transmission through a highly imperfect, noisy physical environment. To manage this, the syllabus moves from continuous signals in networks, signals, and systems to the discrete processing of digital signal processing. Through sampling, a continuous real-world input is broken into discrete pieces of data. Mathematical algorithms, such as the fast Fourier transform, are then applied to filter out interference and extract information. This math is what allows an engineer to clean up the audio of a voice call or analyze the subtle patterns of a biomedical signal. Signal processing is the mathematical translator that allows pristine digital systems to interact with a chaotic analog reality. A parallel track runs alongside the hardware stack. In modern engineering, computing and software design are deeply integrated. Introduction to Computing teaches students the C language, ensuring they have the software tools to control their hardware from the start. Semester 3 introduces data structures, focusing on how to organize information efficiently using dynamic memory and graph traversals. By semester 4, object-oriented programming in Java provides the high-level abstraction needed for complex system design. There was once a strict divide. Engineers built the machines, while programmers wrote the code. Modern engineering requires hardware-software co-design. The two disciplines are now inextricably linked. At NIT Patna, students are required to physically implement their code on custom hardware during workshops. Modern electronics engineering requires the simultaneous mastery of physical silicon and the complex algorithms that command it. In the final semesters, this vertical abstraction stack expands horizontally into real-world technologies. Advanced electives like VLSI design, wireless communication, and the Internet of Things occupy the final 2 years. These final semesters are exactly where the foundations of physics, logic, and software fully merge into real industry-ready applications. This mobile phone is an assembly of inert materials that relies on the entire stack to synchronize, find a signal, and load an interface. The seamless performance of modern technology is a direct result of integrating these diverse engineering disciplines. The outcome of this 4-year degree is the ability to visualize the entire technical pipeline all at once. You understand how an abstract software action creates a high-level command. You see how that command is translated into a specific instruction set for the microprocessor, and you know exactly how that instruction triggers a voltage change in a MOSFET to transmit an electromagnetic wave across the world. The NIT Patna ECE curriculum is an 8-semester study in mastering physical constraints to build limitless digital possibilities.